Hello, my name is Herbert Mączko and I am at the end of my PhD studies in physics at Wrocław University of Science and Technology in Wrocław, Poland, where soon I will be a member of the Department of Semiconductor Materials Engineering. I am going to explore and present some properties of novel quantum wells made of boron-gallium arsenide and gallium phosphide in context of applications as a gain medium that can be integrated with silicon platform. I hope my presentation will show that boron-gallium arsenide and gallium phosphide quantum wells are promising candidates for light-emitting devices and are worth further experimental research and development. Results of theoretical calculations that will be presented were obtained with financial support of the National Science Center within Grant Sonata BIS III and of the National Center for Research and Development within the Polish-Chinese grant. Silicon technology already covers a wide range of microstructures. Silicon finds its applications in guiding and modulating light beams by waveguides and optical modulators respectively. There are silicon photodetectors working in the near-infrared spectrum. Diodes and transistors made of silicon are widely used in everyday objects. Technology currently allows us to create integrated circuits based on silicon, which provides a high density of various based on silicon components. All of this can be found in everyday objects such as computers, smartphones, screens, cars, etc., or more sophisticated devices like this used in telecommunication. Such success of application of silicon in these fields comes from its material properties. However, the properties of silicon itself make it to be a very poor material for light-emitting devices. But why would anyone want to have such devices made of or easy to integrate with silicon? The answer may be for faster computers that are not limited by heating produced by electron transport, for compact spectroscopic chips that can be used for quick medical tests, for some sophisticated and highly repeatable measurements in laboratories. So, light-emitting devices made of silicon or relatively easy to manufacture on silicon are desired. The reason why silicon is a poor material for light-emitting applications is its indirect gap. Despite this fact, some methods of generating light from silicon-based structures are already developed. They utilize simulated Raman scattering processes, rare earth doping, or need creating silicon nanoparticles in silicon-rich oxide layers. In these methods, high pumping power or insufficient efficiencies are main obstacles to make these techniques more popular in daily basis devices. Among semiconductors, 3-5 alloys are already commonly used and well developed for light-emitting applications. However, their lattice constant do not match the lattice constant of silicon, so their direct epitaxial growth on silicon doesn't seem to be the method to have some light-emitting diodes or laser diodes easily. Currently popular and promising method of involving 3-5 semiconductors to silicon-based devices is to attach 3-5 structures by bonding to silicon structures. However, it is a challenging method. The direct epitaxial growth of such structures on silicon would be very welcomed. Some advances have been already made in this field in the past decade. Great progress of development can be seen in growth of germanium-tin alloys on silicon. In some cases, germanium or germanium-tin buffers on silicon are additionally prepared. Here, with proper thickness of germanium or germanium-tin buffer layer, a relaxed surface of very good quality can be achieved for further epitaxy. Many light-emitting and lasing structures have been already presented within this material system, but there seems to be another material system that can be grown epitaxially on silicon. Recent advances in growth technology allow the production of new materials containing boron. From this set of materials, boron-gallium arsenide is especially interesting because growth techniques of gallium arsenide are very well developed. Gallium arsenide is a well-known material from applications in light-emitting devices. Boron-gallium arsenide is a ternary alloy, so the simplest possible kind of alloy within 3-5 semiconductors, and it allows to produce material characterized with a lattice parameter equal to the lattice parameter of silicon. Further, it is worth noting that gallium phosphide is one of 3-5 indirect gap semiconductors that have a lattice parameter very close to the one of silicon. This allows to create gallium phosphide virtual substrates through heteroepitaxy on silicon. Those are the reasons why boron gallium arsenide and gallium phosphide were chosen by our group to analyze them theoretically as the materials of novel quantum wells. The proposed structure is made of a boron-gallium arsenide thin film covered with a gallium phosphide crystal on both sides, all such that can be grown on silicon wafers. Boron-gallium arsenide is a material strained to an unstrained gallium phosphide crystal. The alloy in general can be a direct or an indirect gap semiconductor, dependently on the boron arsenide fraction in the alloy. Whole structure is analyzed as grown along the 100 crystallographic direction of gallium phosphide, which has a specific impact on strain effects. Boron gallium arsenide is lattice matched to gallium phosphide at fraction of boron arsenide equal 23%, but already with 12% of boron arsenide, 10 nanometer wide layers of boron gallium arsenide should be possible to grow. To analyze properties of the quantum wells and to determine their light generation abilities, we calculated material optical gain. The optical gain is a parameter which states about optical amplification properties of given material. The higher the optical gain is, the more light can be produced in a given structure. Few quantities are calculated before the gain. First of all, electronic band structures of quantum wells are computed based on 8K.P model with envelope function approximation. Envelopes are expanded into the basis of plane wave functions. Since barriers of the system are made of indirect gap material and the thin film can be barely direct gap material, a self-consistent approach to the Poisson and Schrödinger equations is crucial and applied. Quasi-Fermi levels are calculated based on neutrality charge condition with two-dimensional carrier density taken as a parameter. Local densities of states are calculated to determine quasi-Fermi levels in each step of the predictor-corrector method of solving Poisson and Schrödinger equations. Material optical gain is calculated within the standard approach based on Fermi's golden rule. Material parameters necessary for the calculations are easily accessible regarding gallium phosphide and gallium arsenide materials. The case is very different for boron arsenide. This material is not fully explored yet since it is not easy to grow in general in comparison to standard 3-5 semiconductors. Some approximations were necessary to conduct the calculations. In case of hydrostatic deformation potentials of the bands at gamma point, only the deformation potential of the direct gap was available. It is put as the deformation potential of the conduction band only in the calculations. Effective mass of electrons in the gamma valley is estimated by fitting parabola to band structures found in literature. Some parameters, however, remained not available. We approximated them by proper values of gallium arsenide, the second binary compound of boron-gallium arsenide alloys. Material parameters of the alloy in most cases are calculated based on Vagard's law. The parabolic interpolation is applied only in case of spin-orbit splitting and energy gap at gamma point, since only for these quantities Boring parameters were available. Blue lines on the charts present the band extremes of gallium phosphide and black lines of the boron-gallium arsenide. It is visible that this system is described with type 1 band offset in a very wide fraction range because gallium phosphide has a much wider direct band gap than gallium arsenide does. Therefore, conditions are favorable for confining electrons and holes around the gamma point of the first brilliant zone in boron-gallium arsenide alloys. However, very close above the minimums of conduction bands in gamma point there are minimums of delta valleys. These valleys are limiting the fraction range in which a thin film layer is useful for light-emitting purposes. Visible splitting of delta valleys is connected with the strain induced by substrate. Pure gallium arsenide grown on gallium phosphide would be strained so much that it would have an indirect gap. Therefore, in this system, boron atoms in the thin film are necessary for reduction strain so that direct gap conditions can be achieved. For this reason, a fraction range from 10 to 35% of boron arsenide in boron gallium arsenide is interesting. Within this fraction range, the critical thickness calculated based on Matthews-Blakesley model is almost always greater than 10 nanometers. This model underestimates the critical thickness, so calculations for thicknesses twice greater are still reasonable. Therefore, chosen ranges of calculations are the range of fraction where boron-gallium arsenide is a direct gap material and the range of thicknesses up to 20 nanometers. First results are shown for quantum wells of thicknesses equal to 10 nanometers and of various fractions. A typical energy profile of the boron-gallium arsenide on gallium phosphide quantum wells at the gamma point is presented on the figure A. It is visible that the thin layer is positively charged with reference to the barriers. The reason for this is that all holes put in the system are confined in the quantum well around the gamma point, while a lot of electrons are located in the delta valleys that allows them to travel through the entire structure. This is visible in the figures B, where three quantum wells are presented, compressively strained with 20% of boron arsenide that is matched to gallium phosphide with 23% of boron arsenide and tensely strained with 26% of boron arsenide. Because of the delta valleys, noticeable electron current leakages in such structures should be expected, and some additional technological solution would be necessary to deal with them. However, arising from this, a positive charging effect allows more electrons to be located in the quantum well around the gamma point, and by this, noticeably strengthening the gain. Quantization effects in the delta valleys are not included in these calculations, so in real structures even less electrons should be localized in the delta valleys around the thin film. Also important features visible in the figures are local densities of states of holes. The highest density close to the band edge is visible for the light holes, of which effect will be visible in gain spectra. Gain spectra for the three quantum wells are calculated for various two-dimensional carrier concentrations. Polarization of the spectra depends on the holes involved in the optical transition. Since the highest density of states close to the band edge occurred for the light holes in the tensely strained quantum well, the gain spectra for transverse magnetic polarization for the quantum well with 26% of boron arsenide have the highest values. Delta valleys seemingly have the most influence on the threshold carrier concentration at which the gain appears. In these quantum wells, holes are always available in the quantum well in much greater numbers than electrons. Delta valleys greatly affect energy of the quasi-Fermi level in the conduction band, so they are the key factor determining threshold carrier concentrations and slopes of peak gain values functions of carrier concentrations shown in the left panel. Strain effects affect the direct gap similarly in both cases of strain, compressive and tensile. However, in the case of tensile strain, delta valleys lower their energies faster than in case of compressive strain, so the usable fraction range for transverse magnetic polarization is narrower than for transverse electric polarizations. Also, because light holes have lower effective mass than heavy holes, the energies of Tm gain are generally higher than these of Te gain. The final description of this system is presented in peak gain max for both polarizations separately. The most promising initial parameters of boron-gallium arsenide on gallium phosphide quantum wells are found to be 8 and 10 nanometers of thickness and 20 and 27% of boron arsenide fraction for Te and Tm polarizations respectively. Structures emitting light of TE polarization should be the easiest to achieve, however higher gain values are found for TM polarization. In conclusion, we proposed a novel quantum well system that can be integrated with silicon technology. It should emit light with wavelength around 690–730 nanometers. Because of delta values, a thin layer should charge positively in reference to the barriers. Theoretically, these structures should be possible to manufacture. Thank you for your attention.